Hello, so this is the second part of the lesson that I'm going to do during the last week of term. So if you were there, you don't need to do this because you have done it with me, but if you weren't, here's a helpful video to go with it. And we're doing the next chapter, part of the next chapter, because if I go through this, then you should be able to do the rest of the chapter on your own. So we're doing 27.1 energy and mass, and then 27.2 binding energy. Just a little question for you to think about. Most people say that maths is invented, but I don't know. It's an interesting point. So here we go, nuclear energy. You've all come across Einstein's famous equation before. And he discovered that the mass of an object increases or decreases when it gains or loses energy. And that goes in accordance with E equals mc squared. Here's an example. A sealed torch radiates 10 watts of light for 10 hours, which is 36,000 seconds. If you use E equals mc squared, okay, that equates to an energy of 0.36 megajoules of energy, so power times time. If you then use E equals mc squared, you can calculate the change in mass, therefore, would be 4 times 10 to the minus 12 kilograms. This change in mass is so small that you wouldn't actually notice, but it does happen, and it's not notable in everyday things like cars moving, all sorts of things that are transferring energy. But if you do nuclei is so small that a very, very small amount of energy can make a change in mass that is significant. Here's a couple of examples for you to have a go at following the same method as before, and then see if you get the right answer. For 2, you need to convert mega electron volts into joules. So remember that would be 5 times 10 to the 6 times 1.6 times 10 to the minus 19. Let's have a look at this in terms of a nuclear reaction then. So here we've got a nuclear reaction. We've got polonium-210 emitting alpha particles and decaying to form a stable isotope of lead-206. Write down an equation to represent this process and calculate the energy released. Now you are given some information in the question. It's important we talk about this information because you won't come across it in this form before. It tells you that the mass is 209.93667 U. Now this U value is the average mass of a proton or neutron, and it's given to you on your data sheet. I think it's 1.67 times 10 to the minus 27. You could convert all of these masses into kilograms, then use E equals mc squared to calculate the energy. However, also on your data sheet, it gives you a really, really helpful shortcut. And it tells you that 1 U is equal to 931.3 mega electron volts. Now, because the amount of energies we're dealing with are very, very small, it's much easier to talk about them in terms of mega electron volts. And then if you need the answer in joules, you can then convert your mega electron volts into joules. So I'm going to show you how to do this problem using the information you've been given. So you can see here that you have a reaction where this polonium is turning into lead by emitting an alpha. And what you might not realise is this nucleus here, if you were to put it on some scales, if you're doing chemistry, say, you would expect the product to equal the reactant. So the reactant here and the product here to have the same mass. But that doesn't happen in nuclei. This polonium, if you put it on some scales, would actually weigh more than if you put these two on some scales. There's a difference in mass. And that difference in mass is because some of the mass is being converted into energy, according to Einstein's famous equation. So let's have a look at this mass. So the change in mass would be the mass of the polonium. So I've put that in. I'm going to leave everything in U now. So I've just written that number in there. Notice the number of significant figures. You need a lot of significant figures because the changes in mass are so small. Now, if I have that as the total mass and I take away the mass of these two, it will give me what's left over. So I'm going to take away the mass of the lead and I'm going to take away the mass of the alpha. And that leaves me with 5.81 times 10 to the minus 3 U. So that is how much mass has been converted into energy. What I'm going to then use is this relationship here to figure out how much energy that is. So the amount of energy will be the change in mass times 931. I put 0.5 there and then 0.3. Depending on where you look, it gives you a different value. So just be aware, on your data sheet, I think it's got 931.5. Anyway, if you do that calculation, you get 5.41 mega electron volts. If you wanted to convert that into joules, you would then do 5.41 times 10 to the 6 for the mega, times electron volts, which is 1.6 times 10 to the minus 19. Equates to 8.656 times 10 to the minus 13 joules. Tiny number, okay, but it is significant in terms of energy. And we know that this releases energy because we know that those alpha particles will have kinetic energy. So why is there this change in mass? Why is this heavier than these two added together? It's to do with the strong nuclear force. So we learned about it in our particles topic. The size of the strong nuclear force can be estimated from the electrostatic repulsion between two protons at a separation of 1 femtometer. And it must be at least the same size to hold the nucleus together. So what it's saying is if you work out the force between two protons that are trying to push each other apart at 1 femtometer, the amount of force required to hold the nucleus together must be the same as that. Otherwise it would fly apart. And if you calculate it, it's about 200 newtons. Now the range is no more than 3 to 4 femtometers because the nucleons are evenly spaced at about 1 femtometer and the force only needs to act on the nearest nucleon. The specification says 0.5 to 3 femtometers. So in order to remove a nucleon from the nucleus, so if my nucleus is here and I wanted to take part of it away, I would have to do work. So I'd have to put some energy in to do that. And the amount of energy required would be using the work done equation. Work done is force times distance. The amount of force I need is about 200 newtons. And I need to move it to a distance of 3 femtometers in order for the strong force not to work anymore. That gives me an energy of 6 times 10 to the minus 13 joules. And then I've converted that to mega electron volts by dividing by 1 times 10 to the 6 for the mega and 1.6 times 10 to the minus 19. So you need about 3.8 mega electron volts to remove a nucleon from the nucleus. Now, the strong nuclear force also has to become repulsive at separations of about 0.5 femtometers or less. Otherwise, if you had two protons here and they got a bit closer than 1.5 femtometers, they would suddenly pull each other in and the nucleus would collapse. That happens in neutron stars, okay, but not in nuclei. So I want you to have a go at these questions, which is asking you to basically use that, work out the change in energy. It gives you here, it wants you to use 1U is 931.3 mega electron volts. It's telling you the rest mass of an electron here, so that must be careful if they use the word atom, because if they use the word atom, they want you to include electrons. If they use the word nucleus, they want you to just do the nucleus. I'll send you a video of how to answer all the questions. So we can then use this idea to work out something called binding energy. So this is now 27.2. If you were to separate the nucleons in a nucleus, you would have to do work to overcome the strong nuclear force. If this is my nucleus, if I want to pull all the nucleons out, I would have to do some work to overcome the strong nuclear force. So the potential energy of each nucleon is therefore increased when it's removed from the nucleus, because I've given it energy, I've pulled it out, so I've done some work, I've given it energy. Now, the binding energy of the nucleus is defined as the work that must be done to separate a nucleus into its constituent neutrons and protons. So you have to remember that definition. It's almost counterintuitive to what you think, because binding you think would mean it's the energy to stick a nucleus together, but it's the opposite. It's how much work you have to do to separate a nucleus into its constituent protons and neutrons. When a nucleus is formed, the energy is released as the strong nuclear force does work pulling the nucleons together. The energy released is equal to the binding energy of the nucleus. So basically, when you make a nucleus, okay, the nucleus releases energy, okay, and the energy released is due to a change in mass. So the nucleus itself, when you make it and pull it together, okay, the nucleons weighed more than when you put them together as a nucleus, okay, and that change in mass is released as energy. And if you want to separate those nucleons back out, you have to put that energy back in. So the mass of the nucleus is less than the mass of the separated nucleons. Strange idea, but very important. So we do something called the mass defect. Now, the mass defect of a nucleus is defined as the difference between the mass of the separated nucleons and the mass of the nucleus. And it's if you want to calculate the mass defect, you need to know some values. So if we look at an atom or a nucleus, it will have a symbol like this, and the top number is the atomic number, which is the number of protons and neutrons, and Z is the proton number. So if you want to know the number of neutrons, you have to do A minus Z, okay, because A is protons and neutrons. So if you do A minus Z, you get the number of neutrons. This gives us an equation of the mass defect as the change in mass when you make a nucleus is equal to the sum of the mass of the protons, so ZMP, plus the mass of the neutrons, so that's A minus ZMN. Okay, so that will give you the mass of the separate nucleons, and they will weigh more than the nucleus when it's made. So you then take away the mass of the made nucleus, and that difference in mass was converted into energy when the nucleus was made. Then you can use that to calculate the energy of the nucleus. You can either use E equals delta mc squared, or you know that if all this is in U, you can multiply it by 931.3 mega electron volts, and then you get it in U. I'm going to go through an example, but I'm going to start a new video so I've got time to do that, okay? So the next video will go through an example of that.